Okay. So yeah, a very, very warm welcome to everyone for our lecture this evening. I'm really, really happy that you could join us. We had, I think, over 90 people sign up across the various meetup groups, and I think about 40 joining us here on Zoom this evening. And I'm really delighted to introduce our speaker today, Professor and Dr. Henrik Norborg. And Henrik currently works as a Professor of Physics at the HSR University of Applied Sciences in Rapperswil, Switzerland. He is also the Programme Director there for Renewable Energy and Environmental Technology. And for the next hour and a half, Henrik will present insights into one of the biggest challenges of our time, and that's climate change. And the current situation we're in, it really offers us some very interesting insights, I think, into the politics and crisis management. And Henrik will explore this in more detail and share his perspectives on what the corona crisis can teach us about solving climate issues. Now, before I hand over to Henrik, I would just like to mention a few housekeeping rules. So the presentation will be about an hour, and it will be followed by time for open discussion and questions. We will have a 5-minute comfort break about halfway through. And we ask you please to keep your lines on mute for the presentation part, and then please remember to unmute them if you want to during the discussion later. We really welcome and encourage your questions, and I suggest that you use the message function in Zoom to raise these or any comments as they pop up. Myself, me and Olena on the call will take these forward into the discussion later. Today's lecture is going to be recorded, and we are planning to post the link afterwards to YouTube and share it with the other volunteers here. If you're comfortable doing so, please leave your cameras on. This will make for a much more colourful event today. And last but not least, I just want to draw your attention to the different views that are possible in Zoom. On the top right, you will see a little toggle button, and you can switch between the gallery view and the speaker view. So that's it from my side. Henrik, I hand over to you now. Thank you very much.
Okay, so thank you very much, Fabienne, and thank you to me and Oleana for organizing this. It's of course a great opportunity. I'm really delighted because I've also been locked down for so long now that I'm getting a bit fed up. So, and of course, welcome to all of you who, despite online fatigue, have taken the time to watch this presentation. I hope it will be interesting. I think it is a very interesting topic, and as I said, I'm looking forward to this presentation. I will, as mentioned, I'm looking forward to your questions too, so please write questions in the chat. I will use the break to review them, and if you have any, and then of course afterwards during the discussion we can also talk about them. You have my contact address here. You might notice this is not my official address because what I'm doing here is kind of semi-official. It's kind of a hobby I have to try to save the world, and it's not yet an official research activity, so therefore I'm using my own layout for the presentations, and I also think it is a nicer layout, by the way. So I'm, as Fabienne said, I'm a physicist. I'm working in the area of renewable energy. I've since a couple of years back, actually I think it's more than 7 years now, I've regularly been giving talks about the climate crisis because I simply was quite frustrated with the slow progress that actually everyone seems to be talking about it, but no one is suggesting a reasonable solution. And I will allow myself to actually suggest a solution towards the end of this presentation. So about the corona crisis, of course, I'm not an epidemiologist. it turns out, however, that my brother is involved in advising the Austrian government on these issues. I've been discussing this quite a lot with him, and so I think I might have some insights into that topic too. So this is the title, "Nature Cannot Be Fooled," and some of you might know this quote. It's actually quite famous. I will give you a short background, and the background is this. In 1986, the American space shuttle Challenger exploded shortly after takeoff. It was a real tragedy. All the crew, of course, killed immediately. And Richard Feynman, the very brilliant and very colorful American physicist, Richard Feynman, was invited to work on this commission to find out the cause of the accident. And he wrote a very interesting personal observation, which made it into the appendix of an official report, where he points out that when he talked to the people who had been involved in this project, it was interesting. The engineers who worked actually had designed the space shuttle. They estimated the risk of a failure to about 1%, so 1 in 100 that the thing would actually fail. The management, the top management who didn't know anything about the technology, they estimated the risk of failure to be 1,000 times smaller. So he thought that was quite interesting because, first of all, how do you come up with such an absurd number? The risk of 1 in 100,000 is simply absurd. And the people who made this estimate, they didn't have any clue about the technology. So how did they come up with it? There are obviously two ways this could happen. Either they simply had no clue, they never talked to their engineers, or they actually allowed themselves to be pressured by politicians to state something that wasn't really true. Anyway, his final remark, which has been, I think it's very well written, is, "For a successful technology, reality must take precedence over public relations, for nature cannot be fooled." Basically pointing out that once you press the start button for this space shuttle, it doesn't matter how much marketing, how much PR you have been engaged in. The only thing that matters if it's correctly designed or not, and clearly in this case it wasn't. So again, we are now facing such a similar situation, because for many years we have been thinking about growing the economy, making business, making money. People have been counting their dividends and returns on investment, and everything went very well. We had a nice economic growth, and then suddenly a very stupid virus comes along. And I don't want to, you can make a very simple model of an infectious disease. I don't want to go through it, but the important point is here that when all is said and done, there are two parameters basically in the equation that determines what is going to happen with this disease. One is the reproduction number. Many of you might have heard about it. It's the R0, which tells you basically how many people is one person going to infect. And the other is Q, is the part of the population that has already been exposed to the virus, and 1 minus Q is then the susceptible part of the population. The problem with the coronavirus, which experts realized very quickly, was that this R0 is about 4. And if you don't do anything. And if R0 is 4, that means that 3/4 of the population has to be infected before we can, before the number of cases will start dropping. And clearly, that would be very difficult to handle. Now, this is a very simple model. You can find much more complex models on the internet, but they don't really contribute anything, because this is the main point. And of course, everyone realized, I mean, we can't allow that to happen. We have to react, because, and I'm sure many of you have seen these plots about flattening the curve. If we don't do anything, the number of infections will rise very rapidly. We will have a very large number of people in intensive care. The healthcare system will not be able to handle that. However, if we manage to reduce this coefficient, we will actually flatten this curve. the number of people that are infected at once will be much lower, and it will be easier to handle. There are no dollars or money or anything entering into this equation. This is simple, the physics of, or the realities of how infectious diseases spread. And of course, people panicked, and I think it was good to panic, because they realized, and this is actually good news, so society reacted. They realized we have to do something. We cannot allow this disease to spread like that. That would be a disaster. They didn't really know how to do it. No one had experience with this, and this R0 depends, of course, a lot, not only on the virus, but very much on our behavior, how much contact, how much interaction we have. So they started improvising. They closed down cinemas, they closed down sport events, they closed down concerts, they closed down schools, they closed down shops. They really didn't know which of these measures would be really effective, but let's try it, because it is clearly better to err on the side of caution. If you close down too much, then the number of infections will drop faster, and it's much easier than to sort of open up society slowly. How if you don't stop the spread of a disease, at some point it will simply be too late, and we will not be able to control it anymore. I think the coronavirus, and I must say I was really impressed by this. It shows that drastic measures are possible. I have been talking about forcing people to fly less for many years now, and everyone told me that that's impossible, can't be done. And then Donald Trump says he doesn't want people to fly from Europe to the United States, and from the next day on, people don't fly from Europe to the United States. You can actually, or if someone had told me that government will simply close down all shops, if someone had told me that in December last year, I would have laughed and said that won't happen. Apparently it does happen. And this is an important point. I don't want to go too much into the details of economy. Governments can never run out of money. They can actually print money if they need to. So you can do something. The important point is, of course, that the acceptance of this is important. I heard on BBC an interview with Giuseppe Conte, the Prime Minister of Italy, and he got this question, shouldn't they have acted faster? And his response was, and I think it was a very thoughtful and probably correct response, is that, look, it wasn't possible to act faster, because until people really realized that we had a real problem, it wouldn't have been possible to close down all shops. You really have to make people realize that we have or everyone has to realize that we have a problem, then you can act. Then, of course, there is the Grim Reaper effect. I think people are still scared of death, which helps. And politicians, of course, even the most cynical politicians realizes that killing your own voters is probably not a very good idea. Thus, they actually acted. But I think the important thing here is you can actually act. And the other thing is scientists do not decide what to do. What the scientists did, and that is fairly easy to show, is that basically telling, look, if you don't act now, you will soon have very, very many people ill, very many people in this intensive care. Hospitals will be overwhelmed, but it's your choice, obviously. And politicians, they basically act when society acts. When there is a big acceptance in society for doing something, then something happens. So, unfortunately, I think we have a much larger emergency at hand, and that is climate change. And I want to give you a very short background to the climate change, because I think it's important that everyone realizes that, again, here it's not really a matter of science anymore. So this slide, I think, is very nice. I've borrowed it from the skepticalscience.com, and it basically shows the history of climate science. And the history of climate science starts in 1824 with Joseph Fourier, who basically calculated that the planet was about 15 degrees warmer than it would have been without an atmosphere. If you just had a a piece of rock at this distance away from the sun, then the planet would be by, well, 15 degrees or something colder than it is today. Or I think it's even more, perhaps it's minus 15. But the exact number doesn't really matter. The important point is that it's there is something to be explained here. And he postulated that it must be the gases in the atmosphere that insulate the planet. And how can we check that? Well, we can measure the absorption of infrared radiation in the atmosphere. And if you do that, people did that in 1859, and lo and behold, it turned out that carbon dioxide, all the molecules with 3 or more atoms, like water vapor, carbon dioxide, methane, etc., were very good at absorbing infrared radiation. Based on this, in 1896, so this is more than 120 years ago, Svante Arrhenius made his first climate model, and he calculated that obviously if we increase an amount of carbon dioxide in the atmosphere, then temperature will increase. So in 1960, Keeling started measuring the so-called Keeling curve. He actually started measuring the carbon dioxide concentration in the atmosphere. In 1988, James Hansen gave his testimonial to the American Congress, telling them basically that it's clear that there is man-made climate change. NASA there's no doubt from research that this is actually happening. 1992, the world decided to solve the problem. This was the United Nations Framework Convention on Climate Change. And in 2015, we had the Paris Agreement. This plot, I think, is very important. I've shown it also on my blog. So this is from an internal report at the Exxon oil company from year 1982. They also got the message, so they started doing their own climate modeling, and they concluded the same thing as everyone else. So they did this in the 70s, so this report was finished in 1982, and they basically predicted that in 2020 the Earth will be 1 degree too warm, and in 2050 it will be about 1.8 degrees too warm. So they were right on the money. So it's quite impressive, isn't it? So oil companies knew already 40 years ago that the Earth would be 1 degree hotter today. Obviously, we could have acted 40 years ago if we had wanted, because everything was known. Climate science hasn't actually provided any new, truly important information for the last 40 years, because we knew already then that we needed to act, but nothing happened. And you can speculate about the reasons. Obviously, short-term thinking and greed is common. I also think that scientists are not very good at communicating. Scientists tend to have this belief that if you make even more complex models and generate even more data, problems will be solved. Unfortunately, they will not. And I put this on my blog, actually. There's a link to this. The Guardian magazine had an article about this. Now, so what is the situation today? So what I have allowed myself to do is to plot the blue curve, and this is publicly available data. I will upload this video and the presentation to my website, and I will also put in the references there. I think it clutters the presentation if you put in too many references here. Anyway, this is official measurements of the carbon concentration of the Earth's atmosphere since 1958. The oscillations you see here, it's the breathing of our planet. So this is winter, summer. And you see there is it's increasing quickly, and the rate of increase is increasing too, unfortunately. We are currently at 416 ppm, parts per million of carbon dioxide in the atmosphere. The reference value is 280 ppm. So before industrialization, we were at 280 ppm, meaning that we have increased basically by 50% since then. And every 1 out of 3 carbon dioxide molecules in the atmosphere are now put there by us, by human activities. It's amazing how fast this goes. So when I started university around 1986, we were only at 350 ppm. So this is going up fast. And I think this is the shocking part, because we, in the 60s, this curve was only increasing by 0.8 parts per million per year. Today, we are increasing 3 times faster. So not only is the concentration increasing, the annual rate of increase is also increasing. And if you look at, I allowed myself to put in, so this is the United Nations Framework on Climate Change, where they basically decided, well, we should probably do something, but unfortunately they decided that the developing countries are not important, and China and India in those days were developing countries, so it means that China is not covered by this, which was by the Kyoto Protocol that happened after this. So in the Paris Agreement in 2050, they basically decided to implement voluntary measures. So the Paris Agreement, if you want to be a bit sarcastic, it basically, you could summarize it as an appeal to all nations to please do something to reduce your carbon emissions. Anyway, we are now here. The limit for if you want to stay below 1.5 degrees with some reasonable probability, we should probably not exceed 435 parts per million. So you see, we have about 20 parts per million to go until we enter the danger zone, and that will happen before 2030 if we don't act quickly. So this 20 ppm, that is an interesting number. I allowed myself to do another plot with this. So the blue dots here, that's the annual carbon emissions, as well, you can get them from different sources. This is from carbontracker.org. And on the x-axis, I have the annual increase of carbon dioxide in the atmosphere, starting at 0.8 in the 60s and 2.4 now. And I mean, most of you would probably agree, you can fit that quite nicely with a straight line. The slope is 17 gigatons per parts per million. So if you add 17 gigatons of carbon dioxide into the atmosphere, then the concentration increases by 1 parts per million. And I said we still have 20 parts per million to go, times 17 gives 340 gigatons. And that is basically the plus minus, give or take, the carbon dioxide budget for 1.5 degrees. Now, what the IPCC and others do is they make these scenarios. And the important point here is that these scenarios, there are very many different models. The big uncertainty here is not the climate modeling. The uncertainty is how much carbon dioxide will actually be produced by mankind. So, and since I don't know that, they have looked at different scenarios, and the ones that would be sort of compatible with our survival would be this scenario here, where we end up with 0.9 to somewhere between 0.9 and 2.3 degrees centigrade. That is, if we don't exceed 430 to 480 parts per million. And all the other scenarios would be pretty awful. Now, the problem that I have with these plots is, of course, the following. The year 2100, they typically end in the year 2100. That's 80 years from now. My father is 88. What that means is that many young people today, like my children, they're born shortly after the year 2000. They can expect to live until 2080, 2090. And to them, it's of course highly relevant what is happening here. Or to put it differently, there are very many people alive on this planet today who will actually live through the year 2100. And to them, it's very important what is going to happen here. So the goal is actually quite clear. We need to cut emissions by at least 7.6% every year for the next decade. Well, actually, we have to continue even after the next decade in order to have any chance of meeting the 1.5 degree target. If we rely on the unconditional pledges made in Paris by different nations, we will end up with about 3.2 degrees temperature rise. And to me, this means that the people who actually go striking today, who go protesting, I mean, it's highly relevant to them because they simply want to survive, and not all of these scenarios are compatible with human survival. So are we on track? Well, obviously not. This is again the kind of, these are carbon emissions. This is from the IPCC SR 1.5 degree report, the special report on the 1.5 degree target. These are the carbon emissions, annual carbon emissions, that how they have to develop in order to stay below 1.5 degrees. And it's fairly easy to remember. You need a 50% reduction by 2030. So in the next 10 years, we have to reduce carbon emissions by 50%. And we need 100% reduction by 2050. So in the next 30 years, we completely have to go carbon neutral. Isn't that realistic? Well, not if you ask BP. So BP, everyone knows BP, it's a major oil company. Of course, they are in the business of selling oil. They are kind of biased, but still they know something about the energy sector. And to them, if they monitor the trends, they basically argue that the evolving transition, which is actually happening now, means that in 2040, emissions will be somewhat higher than they are today, actually quite a bit higher than they are today. They also talk about the Paris Agreement, that this would be this development of this of carbon emissions at least, but they don't really see that happening. Now, this is very worrying, not only because BP actually knows something about the energy market, but also because this is their business plan. If you're an oil company, you have to plan ahead, and investments in expensive infrastructure, you have to plan at least 20 years ahead. So if they are convinced that the demand for fossil fuel is actually going to increase for the next 20 years, they are of course in the process now of building the infrastructure that would be required to produce that fuel. So, and once they have built that infrastructure, they're not going to let it be unused. So it's very worrying that the oil companies see the world differently. Okay, so here, this is another plot that I have made myself. This is, you can get this data. Here is the link, and if you have a good plotting program, you can play around with it. So I did this, I update this regularly. So this is fresh data. The black curve is the annual temperature averages, annual averages. The red curve is the same data smoothed over 11 years. So it's a bit smoother than that. The green line is a simple linear fit to the last 30 years. And you see our planet is now warming by 0.2 degrees per decade. And actually, of course, that was a bit of an outlier, perhaps, I hope so. March 2020 was 1.43 degrees too hot. So the first 3 months of this year were very warm. So, and I think anyone who claims that there's no evidence that the planet is warming should simply have a look at this graph and probably realize that yes, it is warming, and it is warming fast. And the consequences are, of course, spectacular and scary. This is from Washington Post. The average temperature in January this year in Northern Europe, it's in Fahrenheit, so it's not quite as bad as it would have been if it were in centigrade. But anyway, you see parts of Scandinavia, Sweden, Finland, and large part of Russia were like more than 10 Fahrenheit, so more than 5 degrees centigrade too warm in January. Unprecedented. In Sweden, because I'm Swedish myself, southern Sweden hasn't had a winter for 3 years now. Then we have other things. Of course, climate is not the only thing. This I only have this in German, this plot, but anyway, there was a study in 2017 that the number of species at the coast of Sweden, in the waters around Sweden, had decayed by 60% during the last 70 years. There's 60% less animals there, or species. Of course, most of you have seen this discussion about the decline in the insect population, more than 75% decline of 27 years in the insect population. Of course, we have the plastic in the oceans. The sixth extinction, we are wiping out wildlife. This I also got from the Washington Post, basically stating that if we are going to stop using fossil fuel, we actually have no clue how to feed the planet. So we don't know how to feed the planet without frying it. No one seems to really care about that. And Antonio Guterres had made this remark, I think it was quite nice, that the school children, he was talking about the strikers, of course, have grasped something that most of the others don't seem to have understood. We're actually in a race for our lives, and we are about to lose this race. Okay, so now, why is this so difficult? So now let's see if the first poll works. So I wanted to give you some energy statistics, and the first question is, and I don't know if Oleana, if you can start the first poll, is what percentage of global energy demand is covered by fossil fuel currently? And okay, so it's a very erudite crowd here because most of you got it right. It's actually 85%. So if you look at the energy statistics, and again, I borrowed this from BP, this is how we produced energy. This is the energy, how we covered our energy demand in 2018. 34% is oil, 24% is natural gas, 27% is coal. The remaining parts are, the remaining 15% consist of nuclear energy, 4%, hydro energy, 7%, and 4% renewables. So renewables meaning solar and wind. So we are 4% renewable, 85% fossil. To make things worse, if you look at the data, and now it's of course, one thing I've learned is you should only believe statistics that you have sort of manipulated yourself, because you can plot whatever you want. Everyone is talking about how fast renewables are growing. And it's true, if you look at the relative rate, so the percentage of growth, or the growth rate, it's of course very high for renewable because they basically start at zero. But this is the sad truth. In 2018, the world added 826 terawatt hours of renewable energy and about 4 times as much fossil fuel. So actually, if you look at the absolute numbers, fossil fuel generation or generation of energy through fossil fuel is growing 4 times faster than the renewables, which is kind of shocking, I think. Anyway, so now this data, I'm testing this for the first time here because I think it's kind of amusing. I have borrowed some data here. This is the red curve is the carbon emissions worldwide, global carbon emissions in gigatons per year. The blue curve is global GDP, and the black curve is global energy demand. And first you see they all are increasing, of course. You can see that the slope, basically the energy demand and carbon emissions are basically parallel. The slope, the GDP is growing a bit faster. But what I found amusing was that there's clearly something happened in 1973 to all these curves. And it's quite amazing. So what happened in 1973 was that oil prices increased by roughly a factor of 4. This was the oil crisis. And the world reacted to that. Carbon emission had previously been growing by almost 5% per year, and suddenly it dropped to 2% per year. The annual economic growth also dropped from 5.5% per year to 3% per year. and it never recovered. Now you can argue what happened. One thing, some of you, many of you might have heard the story about how the OPEC countries decided to earn more money and raise the price of oil. I also believed that until recently, until I started reading a very interesting book, Oil, Power and War by Matthew Asano. And he pointed out that probably something else happened. There was an American geologist, Hubbert, who predicted in 1956, he made a prediction for peak oil. He was basically saying that he predicted then that the United States would run out of cheap oil in beginning of the 70s. And that happened. And immediately the trade balance of the United States was in the red, because America still had lots of oil. They had in Alaska, they had lots of oil in Alaska, they had in the oceans. Of course, we know they had shale gas and fracking, etc. But there was no way of extracting that with the current oil prices. So the speculation, and I think it's probably true, that America loved it, that oil prices went up, and actually it turns out, yes, the OPEC nations reduced their production, but the production of the United States dropped even more. And basically this saved the American oil industry, because they would have completely been wiped out with the low oil prices that we had before 1973. Okay, so I think this is a good time for an intermission. If you have any questions, please let me know. And let's take 5 minutes break.